Hello, my name is Advik Karanne, and today I would like to present my research that I've done on an optimization for computing transcendental numbers using Zeckendorf's theorem. This year marks the 100-year death anniversary of Indian mathematician Shrinivas Ramanujan. He was best known for his work in number theory and infinite series. In 1914, he discovered a formula for computing pi that would converge rapidly. This formula would later be used in other famous formulas for computing pi, such as the Borwein-Plouffe formula, which is also known as the BBP formula. The BBP formula can be used to calculate the value of pi as well as the nth digit of pi in hexadecimal form. When I started my research, I knew I wanted to do a project related to Ramanujan's work, and I decided to focus on his work on pi, which has influenced many famous algorithms for the computation of pi. The primary source of my research was a book called Pi: The Next Generation, a source book on the recent history of pi and its computation. In this book, there were a compilation of famous papers that outlined the history of the computation of pi, recent algorithms, as well as different research that has been done at hinting at the possibility of proving that pi is a normal number. Whether or not pi is a normal number, which is a number that has each digit appearing with average frequency, has been a large area of research. However, after doing initial literature research, I had not found any papers where people had tried to evaluate pi at different Lucas numbers. Lucas numbers are similar to Fibonacci numbers. The standard Fibonacci sequence is 0, 1, 1, 2, 3, 5. A Lucas number is similar except the starting two numbers are different. However, it still follows a similar pattern as a Fibonacci number, where each number is the sum of the two preceding numbers. For example, the sequence with the two starting numbers of 2 and 1 results in the sequence of 2, 1, 3, 4, 7. My engineering goal going into my project was to find a way to accelerate the computation of pi using the Zeckendorf theorem, which I will explain later on, and to find a pair of Lucas numbers that results in a counterexample of the normalcy of pi. In order to derive an algorithm for the standard BBP algorithm, I used the much similar summation of just n as a starting point. The summation of just n is derived to be n plus 1 divided by 2. So using the Zeckendorf theorem, which states that every positive integer can be represented uniquely as the sum of one or more distinct and non-consecutive Fibonacci numbers, I was able to find an efficient way to calculate the summation of I from 0 to 13. By using the Zeckendorf theorem, you can write any number, let's suppose 13, as the sum of two distinct Fibonacci numbers. For 13, these numbers are 8 plus 5. You can calculate the summation of 0 to 8, which we can calculate by using the given formula, and we can calculate from 1 to 5 and shift the summation by 8. The fundamental concept of my idea is that both the pre-computation done for 13 and the shift are performed exclusively with Fibonacci numbers and not any random number. Because this set of pre-computed numbers is finite and small, this can be done appropriately and stored. You can see the example that by shifting the second series by 8, we perform exactly the same mathematical sum, but we do it from 1 to 5 rather than from 9 to 13. And because 5 is the sum of the previous Fibonacci numbers, this method can be implemented recursively for further optimization. The 100th Fibonacci number is approximately 354 quintillion, so if you store the values of the summation in between 0 and the 100th Fibonacci number, you can find any intermediate and future values in a much more efficient manner as compared to trying to find the 400 quintillionth digit of pi without relying on pre-computed values. This technique will also allow people to check algorithms in a much more efficient way since they will not have to calculate all the digits from scratch again. We have in a way moved from large numbers occurring in the limit of the sum to the inside of the series. This reduces the computation significantly as evident in my data. Using the basic series of n, that led me to try this implementation to the standard BBP algorithm. I use the same technique of storing pre-computed Fibonacci numbers and the shifting technique as described in the summation of just n to the standard BBP algorithm. I denoted my algorithm as the Zeckendorf BBP algorithm. My algorithm is based on the idea of pre-storing the summation of Fibonacci numbers. Since with the Zeckendorf theorem you can break any number as the sum of Fibonacci numbers, you can use pre-computed values and use the shifting technique to compute any intermediate and future numbers. This makes the Zeckendorf algorithm highly efficient as compared to the standard BBP algorithm. In order to determine whether or not this was in fact more optimized when implemented on a computer compared to the standard BBP, I implemented my algorithm in the Java programming language using the big decimal class. I used the shifting technique I talked about earlier and pre-stored the Fibonacci numbers value from the time trials. For example, if I wanted to compute the series of the BBP from 0 to 34, I would look up the pre-stored pi value from 0 to 21 in my data structure, and then compute the BBP series from 0 to 13 with a shift of 21. I changed the upper limit of the series to be different Fibonacci numbers for each trial. For example, I would set the standard BBP as being from 0 to 3, 0 to 5, 0 to 8, and so on and so forth. I then measured the amount of time it took with the Zeckendorf algorithm by using the previous Fibonacci numbers value. In the graph, you can see that the Zeckendorf algorithm in red is much more optimized than the standard BBP algorithm. And this is due to the fact that since you're pre-storing values and using the shifting technique, you will have to do a much smaller amount of iterations as compared to the standard BBP algorithm. This approach can be implemented to all numbers. For example, if you want to calculate the series from 0 to 100, you can calculate the series from 0 to the nearest Fibonacci numbers, and then add the second series with a shift to compute the rest. I then tried to implement the Zeckendorf algorithm to the series for E. You can see that the same idea of the shifting technique in this series as well, except rather than recomputing the series from 0 to 6,765, since 6,765 is a Fibonacci number, we can look it up in our table of values. However, the Zeckendorf algorithm was not as efficient as compared to the original series. After a certain Fibonacci number, the amount of time it took for the Zeckendorf algorithm was larger, and this largely can be attributed to the fact that there's a factorial in the denominator. Since we're dealing with big integers and factorial is expensive computationally, the shifting technique makes the denominator larger, and it is likely the reason that the computation of the Fibonacci numbers in the denominator is taking the most amount of time. Overall, this Zeckendorf algorithm was much more efficient for calculating the nth digit and the value of pi in the Zeckendorf algorithm, since there were no expensive computations when you implemented the shifting technique in the standard BBP algorithm. A second area of research of mine was finding a starting pair in a Lucas sequence that resulted in a counterexample of the normalcy of pi. According to my literature research, no one has tried to evaluate the nth digit of pi with different starting Lucas numbers. I use the standard Fibonacci sequence, or the Lucas sequence, with the starting numbers as 1, 1. I calculated the nth digit of pi using the standard BBP and counted the frequency of every hexadecimal digit. I ran it for 45 terms, which took approximately 17 days. This sequence avoided the digit d up till the 45th term, which is already close to the 3 trillionth digit of pi. I then ran the Lucas sequence with the starting numbers of 3, 1, and sampled the frequency. This can be seen in the following data table. I then got the nth digit of pi using a normal sequence. For example, I would get the first digit of pi, the second digit of pi, the third, the fourth, and so on and so forth, and count the frequency in the hexadecimal digits. I then graphed both tables in a histogram. You can see that the distribution of the graphs is very different. This, in conjunction to the fact that I was able to avoid the digit d with a specific Lucas sequence, hints at the fact that there may exist a Lucas number that results in a counterexample of the normalcy of pi. An adjustment I would have liked to make to my research would have been to try more factorial algorithms in order to optimize the algorithm for the series of E. I would have also liked to try more Lucas sequences. However, since it was taking a lot of computational time, this was very difficult to accomplish with my current machines. A future research of mine is to continue finding more Lucas pairs that can result in a counterexample of pi, and I hope to use my optimized Zeckendorf BBP algorithm to find such a counterexample. My favorite part of doing my project was finding the different ways that the computation of pi has evolved over the last hundreds of years. I also really enjoyed reading about how computers have helped evolve these algorithms and how they've enabled us to continue finding more patterns and digits of pi. I really enjoyed the ability of computing computer science in my mathematical research, and I'm planning on continuing to do research in the field of mathematics next year in the fall as well. Thank you for listening to my talk on an optimization for computing transcendental numbers using Zeckendorf's theorem.